In the previous video, I talked about two different operating level characteristics. First, we learned about economies of scales, which says that as operations produce more units, it will decrease its costs per unit. And then, after a certain point, where costs are at their lowest, costs will begin to gradually rise again. This is known as economies and diseconomies of scale. We then talked about how operations of different sizes will have different optimal operating rates. For example, where a small factory might be able to produce, say, 100 units at $1,000, a large factory would be able to produce maybe 1,000 units at $500 per unit. In this case, think of Tesla's Gigafactory being able to produce many more and cheaper lithium batteries compared to its competitors. One tool to identify the optimal rate is the break-even analysis. The break-even analysis takes a look at the relationship between cost and output with the goal of determining where total revenue equals total cost. Let's now take a closer look at this cost-volume relationship. Let's start by looking at total cost, which is total cost equals fixed cost plus variable cost. And in order to get variable cost, you multiply quantity times the variable cost per unit. So the variable cost is represented by this line here. So if it costs you $10 to make 10 units, then it will cost you $20 to make 20 units. And we have fixed costs like rent and utilities, which is represented by this blue line. So when we add our fixed costs to our total variable cost, we've now calculated our total cost. All right, now let's take a look at total revenue. Total revenue is calculated just like total cost. Total revenue equals revenue times quantity. So if you sell 1 unit for $20, then you'll be able to sell 10 units for $200. And when we put the two graphs together, we get this. This is our cost-volume relationship graph. Here we say that profit is the difference between total cost and revenue, which means that when you have more revenue than cost, you make a profit. And on the other hand, if you have less revenue than cost, you have a loss. And where these two lines intersect, this is our break-even point, which is where our total revenue equals total cost. And listed here are the important formulas relating to evaluating alternative capacity scenarios. The first formula will give you the profit or loss amount under specific circumstances. The second one will let you know how many widgets to produce in order to make a certain amount of profit. And then finally, the third one will let you know what the break-even point is. In other words, where total cost equals total revenue. Let's see these formulas in action using an example that can be found on page 203 of your text. The owner of old-fashioned berry pies is contemplating adding a new line of pies, which will require leasing new equipment for a monthly payment of $6,000. Variable cost will be $2 per pie, and pies would retail for $7 each. So up here we have all the relevant formulas that I would include onto my cheat sheet. And before we look at the question, let's first look at what was given to us. So first of all, we know that our fixed cost is $6,000. Our variable costs are $2. And our revenue per pie is $7 each. All right, let's look at the first question. The question asks us how many pies must be sold in order to break even. And because we're looking at a break-even point, looks like we'll be using the break-even formula. All right, so let's start building the formula. And we're searching for the quantity of the break-even point, which equals 6,000 minus 7 minus 2. That gives us 6,000 over 5. And so the answer to this question is 1,200 pies. So in order to break even, where total cost equals total revenue, we need to make 1,200 pies a month. So the question asks, what would be the profit or loss if 1,000 pies are made and sold in a month? And we're dealing with profits, so we'll be using this formula. P is for profits. And the problem tells us that we're going to be working with a quantity of 1,000 pies. So therefore Q equals 1,000. And now we're ready to solve for P. Okay, so P equals 1,000 times 7 minus 2 minus 6,000. 7 minus 2 is 5. So 5,000 minus 6,000, which gives us a profit of negative 1,000, which means that if we sold 1,000 pies a month, we would be at a loss of $1,000. The next question, how many pies must be sold to realize a profit of $4,000? How many pies means we're dealing with quantity. This time we don't see any reference to a break-even point, so we're solving for Q, which is this formula. And then it's the same drill as before, with profit being $4,000. So P equals 4,000. All right, let's do this. So Q equals 4,000 plus 6,000 divided by 7 minus 2. That gives us 10,000 divided by 5. And so Q equals 2,000 pies. To answer this question, 2,000 pies must be sold to realize a profit of $4,000. And then finally, if 2,000 pies can be sold and we have a profit margin of $5,000, what price should be charged per pie? So 2,000 pies can be sold means we have quantity of 2,000, and profit means P equals 5,000. And we're solving for R because we're looking for a price to charge each pie. And then looking at our option of formulas, we see that we're not dealing with the break-even point, so let's scratch that formula out. And then we're left with the last two formulas. Either of these formulas will solve for R, but I would probably use the first one just because it's easier. But for the purpose of this example, I'll solve for both. Okay, so 2,000 equals 5,000 plus 6,000 divided by R minus 2. So that gives us 2,000 R minus 4,000 equals 11,000. Let's take out the zeros, which gives us 2R equals 15, and R equals $7.50. All right, and now solving with the other formula. So we have 5,000 equals 2,000 times R minus 2 minus 6,000. Let's go ahead and take out all the zeros, which gives us 5 equals 2R minus 4 minus 6. 2R equals 15, and once again, R equals $7.50. So if our plan is to sell 2,000 pies, and our goal is a profit of $5,000, then we will need to price each pie at $7.50.